The sun. It bathes our planet in light and warmth, providing the essential energy that sustains life on Earth. But you know, our star is capable of incredible power, far beyond just lighting up our days. This power sometimes erupts in brilliant flashes, creating spectacular displays of energy. We call these flashes solar flares, and they are among the most powerful events in our solar system. They are sudden, intense bursts of energy that can affect space weather and even impact Earth. Solar flares remind us that the sun is a dynamic and powerful force, constantly changing and evolving. Imagine a billion atomic bombs exploding at once, releasing an unimaginable amount of energy. That's the energy released by a large solar flare. These events are awe-inspiring and humbling. They are also a stark reminder of our reliance on the sun for life and technology. Understanding solar flares is crucial in our technological age, as they can disrupt satellites, communications, and power grids. Solar flares originate from the sun's magnetic field, which is a complex and dynamic system. This field is constantly changing, creating the conditions for solar flares to occur. When magnetic field lines twist and reconnect, they release tremendous energy in the form of a solar flare. This energy is what we see as a solar flare, a brilliant and powerful burst of light and radiation. These events are a fascinating area of study for astronomers who seek to understand their origins and impacts on our solar system. The sun's surface is a chaotic place, a realm of constant turmoil and activity. It's a churning sea of plasma, a superheated state of matter that defies our earthly experiences. This plasma is in constant motion, driven by the sun's powerful magnetic fields, which are invisible yet incredibly influential forces. Think of these magnetic fields as giant rubber bands, stretched and twisted within the sun, storing immense amounts of energy. Sometimes, these rubber bands snap and reconnect, a process known as magnetic reconnection. This releases a tremendous amount of energy, like a slingshot launching a pebble into space, but on a much grander scale. This energy bursts forth from the sun's surface in a spectacular display. We witness this burst as a solar flare, a sudden flash of brightness. The energy released in a solar flare is mind-boggling, a testament to the sun's incredible power. It's equivalent to millions of hydrogen bombs exploding simultaneously, a force beyond human comprehension. This energy travels at the speed of light, reaching Earth in just over 8 minutes, a journey across the vast expanse of space. The effects of this energy on our planet can be significant, impacting our magnetosphere and even our technology. Sometimes this energy creates beautiful auroras in the night sky, a visual reminder of the sun's influence on Earth. However, it can also disrupt satellite communications and power grids, showing the dual nature of solar energy's impact. Not all solar flares are created equal. Astronomers classify them based on their brightness and X-ray wavelengths. This classification system helps us understand the potential impact of a flare. The smallest flares are A-class, followed by B, C, M, and X. Each letter represents a tenfold increase in energy output. So an X-class flare is 10 times more powerful than an M-class flare and 100 times more powerful than a C-class flare. Within each class, flares are further categorized by a number from 1 to 9, with higher numbers indicating greater intensity. An X2 flare is twice as intense as an X1 flare, for instance. The most powerful flares, like the X28 flare in 2003, can disrupt communication systems and even damage satellites. Solar flares can have a significant impact on Earth's technology. When a flare erupts, it releases a stream of charged particles. These particles travel through space at incredible speeds. Earth's magnetic field usually protects us from these particles. However, a powerful solar flare can overwhelm our defenses. These charged particles can then interact with our atmosphere. This interaction can disrupt radio communications, GPS systems, and even power grids. In 1989, a powerful solar flare caused a major blackout in Quebec, Canada. Millions of people were left without power for hours. This event served as a stark reminder of our vulnerability to space weather. As we become increasingly reliant on technology, the potential impact of solar flares grows. Section 5. Coronal mass ejections, riding the solar wind. Solar flares are often accompanied by coronal mass ejections, or CMEs. CMEs are massive eruptions of plasma and magnetic field from the sun's corona, the outermost layer of its atmosphere. Imagine a billion tons of solar material hurtling through space at millions of miles per hour. When a CME reaches Earth, it can trigger intense geomagnetic storms. These storms can disrupt satellites, communication systems, and power grids. They can also create stunning auroras, the northern and southern lights, as charged particles interact with Earth's atmosphere. While CMEs can be disruptive, they are also a source of fascination for scientists. Studying CMEs helps us understand the sun's complex behavior and improve our ability to predict space weather events. Section 6. The Carrington Event, a stark warning from the past. In 1859, the most powerful solar storm in recorded history struck Earth. This event, known as the Carrington Event, was named after the British astronomer Richard Carrington, who first observed the solar flare that caused it. Known as the Carrington Event, this storm caused widespread telegraph system failures. The storm's intensity was so great that it created auroras visible as far south as the Caribbean. Operators reported sparks flying from their equipment, with some even receiving electric shocks. The telegraph systems, which were the backbone of communication at the time, were severely disrupted. Some operators were able to continue sending messages even after disconnecting their batteries, as the storm-induced currents powered the lines. The Carrington Event serves as a stark reminder of the potential power of solar storms. The energy released by such storms can have far-reaching effects on our planet. If a similar event were to occur today, the consequences could be catastrophic. Our reliance on technology makes us more vulnerable to the effects of solar storms. Our modern power grids, communication systems, and satellites are far more sophisticated and interconnected than those of the 19th century. A powerful solar storm could potentially knock out power grids, disrupt communication networks, and damage satellites. The Carrington Event highlights the importance of understanding and predicting solar activity. Scientists are working tirelessly to develop better prediction models to forecast such events. By learning from the past, we can better prepare for the future and mitigate the risks posed by our star's powerful eruptions. Investing in research and technology to predict and protect against solar storms is crucial for safeguarding our modern way of life. Scientists constantly monitor the sun for signs of solar flares and CMEs. They use a variety of ground-based and space-based telescopes to observe the sun's activity in different wavelengths of light. These observatories provide valuable data on the sun's magnetic field, plasma eruptions, and other phenomena. By analyzing this data, scientists can detect solar flares and track their progress towards Earth. One such observatory is the Solar Dynamics Observatory, or SDO, launched by NASA in 2010. SDO provides high-resolution images of the sun every 10 seconds, allowing scientists to study solar flares in unprecedented detail. Predicting solar flares is a challenging task. The sun's magnetic field is incredibly complex, and its behavior can be unpredictable. However, scientists are making progress in developing models to forecast solar activity. These models use data from solar observatories to track the evolution of sunspots, regions of intense magnetic activity on the sun's surface. Sunspots are often the source of solar flares and CMEs. By analyzing sunspot behavior, scientists can estimate the likelihood of a flare occurring. While solar forecasting is still in its early stages, it is a crucial area of research. Accurate forecasts can provide early warning of potentially disruptive space weather events, allowing us to take steps to protect our infrastructure. In our increasingly technology-dependent world, understanding solar flares is more critical than ever. Solar storms can disrupt communication systems, disable satellites, and cause widespread power outages. By studying solar flares, we can develop strategies to mitigate their impact. This includes designing more resilient power grids, hardening satellites against radiation, and developing backup communication systems. Investing in space weather research and infrastructure is crucial for ensuring the smooth functioning of our technological society. As we venture further into space and rely more heavily on technology, understanding and predicting solar flares will become increasingly vital. The sun, our life-giving star, is a source of both wonder and potential danger. Solar flares, those awe-inspiring eruptions of energy, remind us of the immense power of our star. While they can pose risks to our technology, they are also a fascinating area of scientific study. By unraveling the secrets of solar flares, we can better understand the sun's behavior and predict its impact on Earth. This knowledge is essential for safeguarding our technological infrastructure and ensuring the continued progress of our civilization. As we journey further into the cosmos, we must learn to live in harmony with the awesome power of our star.